recording. Let's do what we do. Happy Friday. Thanks. Close this. You watched the video?
Yes.
Nice. And that's what I was going to say. To get to the practice test, you have to mark it complete. Now, that doesn't really mean anything, but just an extra hoop that you have to jump through. And then to see the solutions, you have to mark the practice test complete. Today we're going to go through some practice problems, right, from that video that you have watched. But I also posted, I'll pull up the PDF because the Word document, I don't know how it's going to behave on here, but I posted the PDF of all the different question types that we can have. Okay? And I hate working in Word, but I did make it in Word so that you could have it to work with. So type of question, is it a proportion question or is it a means question? Right? And then you've got options. If you've decided it's a proportion type of question, right, then you can have one sample and you can do a hypothesis test or a confidence interval. You can have two samples and the conditions, you'll notice, are all very similar across the board, right? Two samples or three or more. And I also linked the formula sheets. If you have a means type question, okay, we're only going to stick to one or two samples, but I also posted a bonus assignment on ANOVA, which I don't have a pointer online. So the 3+ groups, we use an ANOVA or an analysis of variance. Okay. And so you're welcome to try that one. It'll replace your lowest assignment grade. And so if you don't do it, it'll just bump it. So that's fine. But for two samples, we have either paired data, right? Two observations on the same subject, right? Or we can have two independent samples. Okay? And so we're going to focus on those two today because that's what you watch the video on, right? But I think I even snuck in a sneak preview, right? For the paired data especially, it just becomes a one sample means type of question for the differences. Okay? And so there's that. I posted that. There's a lot of stuff in this week. And then we've got the test on Wednesday. Okay. So today we're going to do this inference for numerical data practice, which we're doing in class. Looks like this, and we're going to work through it. Okay. Wasn't here. I'll delete this page and I'll just move it down here so that I can write around it better. But first, I guess I should say test number 2 on Wednesday. There'll be slightly more people here then, I think. Let's do a smidge of review of that video. If we have two samples of numerical data, right, measurements, things like that, anything that you can talk about the average for, right, that's numerical data. And so if we have two samples of numerical data, the first way that we could consider these two samples is if they're paired. right? I've got sample 1, sample 2, but they are from the same subject, right? Here, 2 measurements on the same subject. It doesn't have to be the same subject, but the idea is that we're trying to eliminate the variability between between the subjects, or within the subjects, I should say. And so kind of before and after scores are pretty common, right? You write a test before you do some course, and then you write the same test afterwards to see how well you've improved, or how much you've improved, or maybe a similar test, right? So you've got these before and after school scores. Those are kind of the most common. Okay. But anytime that you have made 2 measurements on the same subject, it's considered paired. Okay. And right, I think does the video have Jocko's Garage still? Does it use Jocko's Garage as the example? It's like a suspicious garage, and they get quotes on on the same car, so they suspect that Jocko's Garage is overcharging for his quotes. No, different example. I do think Jocko's Garage is really funny though. Anyway, so they suspect that his quotes are higher than they should be. And so what they do is they take 10 cars, but each car, they take it to shop whatever and Jocko's Garage. And so now you have 2 quotes, right? But for the one car. And if you think about damage done to a car, then there could be a little bit of damage, which would give you a lower quote, of course, just in general, right? Or there could be a lot of damage, which would give you a higher quote just in general, right? But it would be linked to that car. And so that would be paired data, right? We also have before and after scores, right? Maybe it was one of those boring ones.
There was one with like the price of the carrots, but I can't, like the carrots were the gold.
But I think that's 2 independent samples. Yeah. I guess I could look into it's okay. But you've made 2 measurements on the same subject. Then we analyze the mean difference. Oops. I'll clean this up.
I think it was the reading and writing test. Yeah.
Oh, boring. Boring. But then you have 2 measurements on the same subject still. Too bad. I like Jocko's Garage. Maybe I'll bring it back. So the mean difference means that your null hypothesis is about how the mean difference compares to 0, right? If there's no difference between the before and after scores, right, or the 2 quotes from the 2 garages, then the mean of the differences should be 0. Okay? What's nice is once you have picked that this is a paired data type of question, right, or matched pairs, sometimes I call them matched pairs just to emphasize that in case paired doesn't do it for you, right, matched pairs, they match on the subject. And so then once you've decided that you have a paired data type of question, this will always be your null hypothesis. And that's really nice because you don't need to make any changes. For your alternative, you could have not equal to 0, right? Or maybe less than or greater than. You have to spend some time thinking about how you calculated the differences in that case. And so usually I make it a two-sided test for that reason for paired data, just because it's a little bit tricky, right? Because it depends on how did you calculate the difference. If the difference is before minus after, right? If we've got this generic example, right? Then if you want to show that the after score is higher, right? That's a one-sided test. Then you'd have B minus A, and A is higher, meaning you're subtracting a bigger number, which means that your mu diff would be less than 0, right? That's hard. That's hard to do, and not something that I expect you to do in a test situation, maybe on an assignment, right? You kind of have to think about it. But for the test, right, it would be a two-sided test. Okay. But then you'd calculate your test statistic. Maybe I brought this in prematurely. Oh, oops. Your T is the mean of the differences minus your mu diff. Well, your mu diff is just 0, right? We do everything assuming the null hypothesis is true, and so your mu diff would be 0. And I can't remember on our formula sheet, do I have it as 0 or I do? I'll just 0. All right. Divided by the standard deviation of the differences divided by the square root of the number of differences. That's probably the only hiccup, is that your n has to be the number of differences, right? Even though you have two columns in your spreadsheet of data, right? You convert that to the differences, right? And then you've got it zipped up to one sample. Then you're able to calculate your T and your P value using your T, right? The T table. You need your degrees of freedom, right? Degrees of freedom is still going to be n minus 1, but in this case, n is the number of differences. And so we've just tacked on a little diff, right, for the differences on everything. And then it's basically a one sample means type question. For your confidence interval, it's for a hypothesis test. For a confidence interval, you would have x bar of the differences plus minus t star times s of the differences divided by the square root of the number of differences. Right? That's the same as one sample mean, just toss a bunch of diffs on there. Which means what? I need to give you x bar of the differences. I need to give you S of the differences, the standard deviation of the differences, and I need to give you the sample size, the number of differences. That's for paired data. Then we can have two independent sample means, right? If I want to compare these two independent groups, right? So the carat weights of the diamonds, two independent sample means. Right. There's no natural linkage between the two samples. That's okay. We're able to handle that. But that means that we have information from each sample, right? We have a sample mean, we have a sample standard deviation, and then we have a sample size for each of those two groups. And so we have two samples of numerical data with no natural linkage. right? They're independent of each other. And we want to compare those two means. In our hypothesis test, sorry, I'm gonna sit down. Hopefully that's okay. Stay on the line. Oh.
Most professors can stand up the whole class.
Usually I do because I feel like I can like talk better at you, but just feeling a little faint. So.
I actually hate standing for long periods of time. I just can't.
I think I move more than I realize because yeah, same thing. Standing still is like, ugh. But yeah, I don't know. Anyways, hey guys. I feel so short. So then my hypothesis, we've seen this before with two sample proportions, right? We want to compare those proportions. And so we incorporate, well, mu1 minus mu2. How does that compare to 0, right? Or if you prefer, you can use mu1 minus mu2 is or sorry, that's the same thing, is equal to mu2. There. That's the same thing, right? So your alternative hypothesis, I'm actually going to skip it because it can be any of the signs, right? Mu1 minus mu2 is not equal to 0, less than 0, greater than 0. In those scenarios, if you're having a hard time, I do find that this version of the null, or yeah, of the hypothesis is a little bit easier, right? Because then you can look at mu1 and mu2 if you suspect one is less than the other, right? Not equal to is usually fine. Okay, so then we're juggling and we need to have question specific subscripts. Same as the proportions, right? You can't just say P1 and P2. I have to know which group is which one, especially if you have a one-sided test, but just in general, I want to see it in your hypotheses. In your test statistic, it's way too tedious, so you don't have to. You can just use 1 and 2, it's easier. But we need to have question-specific subscripts in the hypotheses. And I bring that up because I was marking another test that I just had, and I wrote that a lot and took half a mark off. Rude. But I said it, I wrote it in red. Now you're gonna do it. You're gonna remember. Okay, so I won't write out the alternative because it can be any one of those 3 signs. As opposed to the paired data, I will use the not equal to. So then our T, just like our Z was a little bit bigger, it has to involve information from both samples, right? The sample means, the sample standard deviations, and the sample sizes. And let's see if I can pull this off. X1 bar minus X2 bar, that's my point estimate, right? My best guess at what mu1 minus mu2 looks like. Okay, I see how far this difference is from 0, but I don't think I have that on the formula sheet. No, I don't even write the minus 0. Technically, that's what we're doing, right? We're seeing how far is this point estimate from my hypothesized difference of 0, right? And so we don't need to write it. Divided by, well, I guess I should have snuck S1 squared over N1 plus S2 squared over N2, but I will confirm that because it's been a while. Score. Standard error. Right. Don't forget those squares. Right. They tend to make a mess, S1 squared over N1 and then S2 squared over N2. But after that, all you really need to find your p-value is the degrees of freedom. Okay. And we are going to, there are a couple of different ways. There's a huge formula for the degrees of freedom that I don't want to use, which Excel would use in the background if you're using any sort of software. But for our degrees of freedom, we are going to use the smaller sample size minus 1, right? And how we write that is the minimum of N1 minus 1 or N2 minus 1. Right? That's the smallest sample size minus 1. But then once you have your degrees of freedom, you can go to your t-table and you can find your p-value just like we've been doing, and you can draw your conclusion. And hopefully when I say draw your conclusion, you understand, like, kind of state the conclusion. I have had students in the past that, what do you want me to draw here? I don't want you to draw anything, just state your conclusion. You can draw it if you want. Okay, and then the confidence interval, right? We have our point estimate, x1 bar minus x2 bar, plus minus a t star, the critical value, right? And then what's really, really nice is it's the same standard error, right? Unlike the proportions, right? Then we had a different standard error for the confidence interval versus the hypothesis test, right? But now for means questions, it stays the same, right? Which is especially beneficial if you have to do both a confidence interval and a hypothesis test, then you can recycle your work. S1 squared over N1 plus S2 squared over N2. These questions, just like two sample proportion questions, I find are relatively easy to pick out because I need to give you a ton of information, right? I need to give you what? Let's see, which ones did I highlight here in the T? I need to give you x1 bar, I need to give you x2 bar, I need to give you S1, I need to give you S2, I need to give you N1, and I need to give you N2. Usually, right? There are scenarios where I type it out, but usually how I communicate it is in a table, right? Because it's going to be a little bit easier. Often the paired data I will also give in a table, but one kind of obvious giveaway is if your N1 and N2 are different, it has to be two independent samples. They're allowed to be the same, right? So that's not a guarantee, but if they are different, then it's for sure two independent samples. Let me, oh, I already added a page, nice. So now, I used to have a platypus test, but it doesn't start with M, which is one of my criteria now. And they're actually really freaky. So
It doesn't start with what?
All my animals start with M. And there's a new animal for test 2. Not a manatee anymore. Let you think on that. I know, like, no, you'll have to wait. Everything in italics, they're just fun facts about platypuses, which I did confirm is the plural of platypus. It's a group of platypuses, which is funny. All right.
I remember facing first thing it's 0.5. I might be wrong.
Well, I made this a long time ago, and at that point I confirmed, but maybe, I think it's potentially one of those where it's like, it can be either. But anyways, I think platypuses is funner to say. Funner.
We're in stats.
Yeah,
This isn't English.
exactly. Yeah, just a lot of words. You overheard some people talking, and they're saying that the platypus releases different amounts of venom if he's provoked or angry, which we're going to call angry, than if he's startled or cornered, which we're going to classify as scared. Naturally and kind of cruelly, you decide to test this theory with a sample of 32 randomly selected platypuses. You decide that they will receive both treatments. Some will be scared first, and some will be made angry first, and this assignment will be done randomly. Suns like a proper experiment. The amount of venom secreted after each treatment is measured in milliliters. A summary of the data you collected is found below. Now, the first thing that you're going to want to do as you read through a question is figure out, okay, what type of question do I have? Right, because all the questions on test 2 are going to be hypothesis testing or confidence intervals. Right, and so then you need to know, well, what type of question do I have? Because that'll let you really focus on your formula sheet, right, where you need to be. Okay, and so your first question that I'll give you is, what type of question is this? Right, you have to tell me what type of question it is. Okay, and that's really just to nudge you in the right direction. And it's an easy 1 mark. Okay. So if you read this question, you can ignore the italics. These are just fun facts. LFFs. Little fun facts. Guess it's not possessive. LFF. Little fun fact. Here's the question. What type of question is this? So let's look at what we've been given, right? And so we have 32 randomly selected platypuses, okay? And they each get this treatment. They get scared and they get angry. So if you think about your Excel spreadsheet, right? So in Excel, what would this look like? You would have, okay, platypus number 1, platy 1, 2, how much venom they secreted when they were scared, and how much they secreted when they were angry. Those are 2 samples, but they're paired on each platypus, right? And so that's why it's a 2 samples, but they're paired on each platypus. I did way more research than I should have to make this platypus test, but not enough to know if maybe there's a difference in different platypuses. Maybe some just excrete a lot of venom and some just don't, right? But that doesn't matter to us, because if we treat it as a paired sample, then we're able to capture that, right? And so that's the reason that we treat it as a paired sample, right? We could analyze these as if they were individual samples, right? And we have that information, right? We have X1 bar, X2 bar, S1, S2, okay? But I also give you the mean and the standard deviation of the differences, okay? Yes, you can get to the mean of the differences, but notice that there's no reasonable way to get to the standard deviation of the differences just because there's a square root and squares involved, okay? So what you need to latch on to is you have the mean of the differences, right? And you have the standard deviation of the differences. Okay? Making this paired data. And how do I? Yeah. 2 measurements on each platypus. And that's the reason. You don't have to give the reason, you just need to tell me the type. That's why I made it a different color. Okay, so here, what we've been given is that X bar of the differences is negative 0.5 and S of the differences is 7.51. We also need the number of differences, which is in the question. 32 randomly selected platypuses. So the number of differences is 32. Okay. I think we're ready for some questions here. Is there evidence that platypuses do in fact excrete different amounts of venom depending on if they're provoked or angry? So angry than if they're startled or cornered, scared. Now, this is where it gets, we're kind of leveling up a little bit. We're going to use a 95% confidence interval to test this hypothesis, right? And so we're kind of connecting those two things now, okay? What's nice is when we use a confidence interval to test a hypothesis, it's a little bit less rigorous, okay? We need to state our hypotheses, which will be what? Once you've decided that it's paired data, right? Let me grab it on your formula sheet so that we have it. Oops. Right. So if we're testing a hypothesis, we should say what the hypothesis is, the null and alternative hypothesis. Oh, you know what I forgot? Should we check the assumptions before we get started? Get them over with. They're the same for confidence intervals and hypothesis tests for means, and so they're a little bit briefer, but fine. Let's get it over with. Step 0. It's pretty bad I started calling it step 0, but it kind of stuck. Check the conditions. What are the conditions? Kind of weird because we have paired data, right? And so our samples, our 2 samples have to be paired. That's one of the conditions, right? It's also kind of implied by the type. So if you don't want to think about that, that's okay. But the independence condition still applies because the platypuses were randomly sampled, right? And so the platypuses that we're working with still have to be considered independent of each other, right? We don't have independence between the 2 samples, but that's because it's paired data. And so platypuses were randomly sampled. So we may assume they are independent. They are independent of each other. Oh. This one's optional, right? Because it's implied by the type. Okay, but we've made two measurements, or the two samples are paired. And then the normality condition. We have, if n is less than 30, then we need to argue that, okay, then, you know, I sampled from a nearly normal distribution, and so it should be okay. Or you can make a histogram of your observations, and if they look nearly normal, then you're good to go. But we have n of 32, right, or n diff of 32, which is greater than or equal to 30. So we may assume normality. Right.
Where did that 30 come from?
It's just we need a large enough sample, even if we're pulling from a skewed distribution. If our sample size is bigger than 30, just as a rough guide, then we're allowed to assume that the means follow a normal distribution.
Okay.
And so it's just a rough guide. I've seen as low as 20 be argued, but we're gonna use 30. And so for means questions, you want to compare your sample size. And if it's bigger than 30, you can just go ahead. If it's less than 30, then you have to argue that it looks approximately normal. Right. Nice. Therefore, the conditions for inference are satisfied. I'll keep it on the next page, otherwise it's too choppy. So if we have to test the hypothesis, we need to state our hypothesis. Now, whether we're using a confidence interval or a full formal hypothesis test, the null hypothesis and the alternative would be the same, right? And so we can say, okay, well, what's really nice is once you've decided that you have paired data, right, then you know your null hypothesis has to be mu diff is equal to 0. Now, for your alternative hypothesis, we are only able to use a confidence interval for a two-sided test, right? Because it has to be symmetric. And so that makes a two-sided test. And so mu diff is not equal to 0. Must be two-sided to use a confidence interval, right? The confidence interval is only kind of equivalent to a two-sided test. But now we can build our confidence interval. X bar of the differences plus minus T star. And I do have the degrees of freedom here, n diff minus 1 as a little subscript, but maybe what we'll do before we go ahead, since I have some space here, the degrees of freedom is n diff minus 1, which is 32 minus 1, which is 31. And where's our t-table? That's what I thought. I don't know why I pulled up the paper one. Should have been going here. I don't know what I was doing here. Probably last day. On our t-table, right, we try to find 31 degrees of freedom, but I am choosing between 30 and 40. There's no risk here, but right, you would probably pick 30. But you always need to round down, right? Even if we had 39 degrees of freedom, right? It's tempting to use 40, but you have to go to 30. Okay? And that's just because if you go to 40, you're saying you have a larger sample size than you do, right? Which then implies that you have more reliable estimates than you actually do, and it's just lying. And so then you go for 30 and you play it safe. Okay? And so what you're going to do is you're going to write, here's my degrees of freedom, is 31, but using degrees of freedom equal to 30 in the table. If you're using Excel, it can handle any, you can just give it the degrees of freedom. But the way I had to set up the assignments is you have to use the same one from the table, otherwise your results might not match. So that would be confusing, right? But you can change it to the appropriate degrees of freedom in Excel. T star times the standard deviation of the differences divided by the square root of the number of the differences. Maybe I'll using the T table, we find T star is what? We wanted a 95% confidence interval. And so here we go for our confidence level, 95. And instead of going all the way down to the bottom, we go to our 30 degrees of freedom. And we find that our T star is 2.042, which is similar to the Z of 1.96, but 2.042. Now we have all the components that we need, right? We have X bar diff, which was way up here, negative 0.5. We have S diff, which was 7.51, or these ones here. Let's jot those down. Negative 0.50 plus minus 2.042 times 7.51 divided by the square root of 32. Right. There's still 32 differences, even though we're only using 30 degrees of freedom, but that's separate. So make sure you keep the 32. It's a pretty common mistake, right? That you get hung up on. Okay, but it's just the N. All right, let's see here. I should have had these Martha Stewarted ready. I put it into the oven and then ta-da. Huh?
Like Martha Stewart or something.
I know.
It's so good.
I like it. Yeah, I should have Martha Stewarted it. Did it.
I play Sims and I made Martha Stewart as one of my characters.
Awesome.
And it also makes me laugh.
Well, they go together. Yeah.
And her hobby in Sims is baking.
Standard error is 1.3276, let's call it. And I need to move out 2.042 of those, right, to make a 95% confidence interval. So times 2.042, and I get negative 0.50 plus minus 2.710944869. Now, what's usually safe, just as a rule of thumb, is if you keep at least as many decimal places as I gave you, right? And so I gave you 2 decimal places, right? Negative 0.50 and 7.51. And so you're allowed to round to 2 decimal places. But it's kind of a bad habit to round more than that, okay? And so this is your margin of error. And I don't know if it's been due yet, but there's a confidence interval, or I think it's one sample proportion where you get used to the question, but sometimes in those assignment questions, it wants the estimate, the point estimate plus minus the margin of error, right? And I always get, it's not working. I know, you're doing it right. It just wants it in a different way.
I had one recently where it just absolutely would not accept one of the numbers.
Mm.
Even though I did it literally like I went online and found a calculator. I think it was like the Z score or something. And it was like I
Oh.
went online and it's like, okay, Z score this. And I'm like, this is the exact same thing I got. And I put it in, it's wrong again. So I'm adding like rounding.
I wonder if it's, sometimes, programming those is kind of tricky.
That one ended up being like 12 marks. I ended up getting like,
If you remember which one it is, I can have a look.
I mean, you can do that now, so it's fine.
They're not there's so many.
I know. It's,
So it's like, but it is annoying when you're like, I got it though, I'm pretty sure. Let's round to 2 decimal places just because I'm being lazy. Negative 0.5 minus 2.71. I get negative 3.21 up to negative 0.5 plus 2.71 up to 2.21 to 2 decimal places. So the procedure for the paired data is not difficult. It's basically the same as for one sample mean. It's the interpretation that's a little bit trickier, right? Because this is now an interval for the mean difference, right? And so this is an interval for mu diff, right, which is the mean difference. So our interpretation has to be about the mean difference, the population mean difference, if I'm going to be picky. The population mean difference. How we start our interpretation, and you have to interpret the confidence interval, right? It's half your marks. So this is only half of it. Now we have to interpret it, but we use the same blurb as always, right? We built a 95% confidence interval. We are 95% confident the interval from negative 3.21 to 2.21 captures the mean difference, or the population mean difference, I should say. And let's see how I'll go rogue. I didn't set this one up. So usually on the test, I set up the question so that you can just reuse the wording, right? And really just take from it. In this one, it's a little bit too long. And I'm feeling lazy, I guess. So we're 95% confident that the interval from negative 3.21 to 2.21 captures the population mean difference in venom secreted. And if I was being proper, when they're scared versus angry or something like that. But so how can we use this to test our hypothesis, right? And so now going back to our null hypothesis is that the difference can be 0, right? It's basically 0. And then when we look at this interval, right? And you can even draw it on a number line if you want, right? Negative 3.21, just a fake number line, 2.21. The null hypothesized difference of 0 is in there, right? And so I'm 95% confident that that's one of the plausible values for the population mean difference, right? And so here, H naught, that mu diff is equal to 0 is one of those options, which means I do not have enough evidence to reject H naught. So how we word that is like this. Since a mean difference of 0 is in the interval, right? And kind of a go-to way of checking it is if you go from a negative value to a positive value, you had to cross 0 at some point, right? So since a mean difference of 0 is in the interval, we do not have enough evidence to reject H naught. Right.
So if 0 wasn't in it, then could we reject it?
Yes.
Okay.
Yeah, because if it's entirely negative, then you're 95% confident that whatever you subtracted is higher than what you subtracted it from. And so in this case, I think we would have done, what was it? Yeah, we did scared minus angry for the differences. And so if it's consistently negative, it means that the angry is consistently higher than the scared, right? Meaning that they do excrete more when they're angry versus when they're scared. Or if it's entirely positive, then it means that the scared is consistently higher than the angry, right? But if it's over 0, then they're, basically the same.
Okay.
Nice. But that's really difficult, kind of conceptually, right? And so, yeah. I expect a lot, but I don't expect that. I just need you to be able to say, okay, well, if the hypothesized value is inside the interval, then I don't have enough evidence to reject H naught. If it's outside the interval, then you do have enough evidence to reject H naught. Therefore, I'll just do a shorthand here to keep it on the same page. No evidence of a significant difference when angry versus scared. I know, cheater version. Part B. We already know the answer to part B, but we're going to do it formally. What you'll notice on that practice for the test, it's practice for the test because there's a lot of practice, right? And so what you'll notice is that I make you do both, of course, on the test. It'll either be a confidence interval or a hypothesis test, right? And in the one sample proportion, I could also make you do a sample size calculation. I'm allowed to do that. But that's the only thing. And so confidence interval, hypothesis test, but only one. But I need to give you practice for all of them. Right? Is there evidence? Now, is there evidence tells me that this is going to be a hypothesis test. Okay. That platypuses do in fact excrete different amounts of venom depending on if they're provoked or angry than if they're startled or cornered. Use a formal hypothesis test with an alpha level of 0.05. Okay. We've already done step 1, which is state the hypotheses. we know that, okay, from the type of question, it has to be mu diff is equal to 0. The alternative, we know already it's that it has to be not equal to 0. That was for the confidence interval, but it's also because we want to know if they excrete different amounts. Now, don't overthink it, but if you had to read this out in words, your alternative hypothesis would be that the mean of the differences is significantly different from 0. Well, don't overthink it. But there's a lot of different differences that we talk about. Right? Now, because I want to know if there's a difference, right, not equal to, then this makes it a two-sided test, which means later in step 3, I'm going to need a two-sided p-value, right? And because they're so disconnected, right, I know I'm going to still have questions saying, how do I know if it's a two-sided p-value or a one-sided? I have to take you all the way back to your alternative. Right? Step 2, I like do the test. Do the test, do the do. But really what I mean is calculate the test statistic. The test statistic is your t, right? And on your formula sheet, right, it's just outlined as, okay, if you're doing a hypothesis test, here's step 1 and here's step 2, and here's what you're gonna need for step 3 is your degrees of freedom, right? And then once you have your p-value, everything stays the same. Okay, so your t is x bar of the differences. Technically, how far is it from 0, right? But I don't, oh, I do have it 0. Yeah, that's nice of me. How far is it from 0? You obviously don't need to write that because it doesn't do anything. Divided by s diff divided by root of n diff. All that information stays the same. You had to check in with your gut here. Do you expect a large t or a small t? Just based off of our confidence interval, I would expect a relatively small t, right? Kind of hovering around 0, right? We already said, well, 0 is in the interval, so I'm not going to reject H naught. And so now, right, my t would need to be really large in order to reject H naught. So I'm expecting kind of a smallish t. All right. Negative 0.50 minus 0, I'm not going to write that, divided by 7.51 divided by the root of 32. Negative 0.5 divided by, oh, maybe I should do my 7.51 divided by the root of 32 is still 1.327, negative 0.5 divided by that guy. Negative 0.3766214547. You need at least 3 decimal places for the t table, right? Because it has 3 decimal places, and so you don't want to get caught up. In fact, it might be safe to use 4, right? 4 might be nice. Okay. This, as I expected, is not very far from 0, right? If we think about a t distribution, it's still centered on 0. And I found something down here, negative 0.3766. Relatively close. It's not until we pass kind of 2-ish, negative 2, that we would start thinking about rejecting H naught, right? We use the p-values, but this is kind of in a reasonable realm of 0. So once you have your test statistics, step 3 is find the p-value. Oh, that doesn't, oh, my eraser. I like to write out everything that I'm doing. I encourage you to do the same just because it kind of also helps guide you along to what you're supposed to do. And so using the T table, why the T table? Because we calculated a T. And because we want a p-value. We've been using the T table for all our p-values, right? Even for Zs. So using the T table with degrees of freedom equal to n diff minus 1, which is 32 minus 1. So the degrees of freedom is 31. And then you have to tell me that you know to round down, but using degrees of freedom equal to 30. We've already done this work, right? But remember, on the test, you'll only have done one of these, right? And so you're not repeating the work. But using 30 degrees of freedom, we use the same setup that we have been using, right? I put my calculated T, my test statistic in the center, right? The absolute value of T equal to negative 3.766. Let's keep 4 decimal places there. As long as you keep at least 3, I'm happy. That value is going to be between two things. So let's see here. I'm going to copy this. Absolute value drops the negative. Okay. What's on the inside track of all these? T is centered on 0, Z is centered on 0, right? And so on the other side here, you could have an imaginary kind of 0 block, right? Now so T, this T negative or 0.3766 is between 0 and 0.683. Right? And so it's between, and I'll write it here, and 0.683. Okay. If you think about your T being centered at 0, and the one-sided p-value is the area in one of the tails, right? Then the one-sided p-value, let's put it in the lower tail, right? Splits it in half, so it must be 0.5. But if you take both the tails at 0, then the two-sided p-value is 1, right? And so here, this is 0.5, and this is 1 at 0. You could have the same scenario over on the other side, right? The next stop is infinity. Yeah. At infinity, the area in one of the tails is 0, and 0 times 2 is still 0. Okay. And so maybe just for completeness, I'll put those there. And maybe I'll do 2 times 0 is 0. Kind of a special case. Okay. It's not until now that we need to remember if we're doing a one-sided test or a two-sided test, right? Which means we have to scroll all the way to the top. And that's why I like to make a note here, because it's so easy to forget, right? But because I have a not equal to here, I have a two-sided test, which means I need a two-sided p-value. So then here, my two-sided p-value is going to be between two values. Now, my two-sided P is down here. I have to read it from right to left, just because as the T's are increasing, the area in the tail is decreasing, but you always have to list them from smallest to largest, especially if you want to preserve this inequality like this, right? So then my two-sided p-value is somewhere between 0.50 and 1, which is really, really large, telling me I do not have enough evidence to reject H naught, right? Same as always. Same as always, she says. I know. Step 4, conclusion. This is your time to show off everything that you know, right? You know that you have a two-sided p-value and you know a range for it, so why not write that down? Since our two-sided p-value is between 0.5 and 1, that's not less than 0.05, right? We were asked to use an alpha level of 0.05. Okay. It is not less than our alpha level of 0.05. So since our two-sided p-value is between 0.5 and 1, it's not less than our alpha level of 0.05, which means we do not have enough evidence to reject H naught. We do not have enough evidence to reject H naught. Therefore, right, what does that mean in terms of the question? Still the same 3 parts, right? You have to tell me what your p-value is, compare it to the alpha level. Is it less than or not less than? Then do you have enough evidence to reject H naught, or do you not have enough evidence to reject H naught? And then what does that mean in terms of the question? Now I'm just going to snag it from here and kind of sneakily reword it as an answer. Therefore, there is no evidence that platypuses do in fact excrete different amounts of venom depending on if they're provoked or angry than if they're startled or cornered. Period. There. Tedious, but not hard. Okay. Nice. And that is the same thing that we found with the confidence interval, right? And so it's just 2 ways of testing the hypothesis. Now, where is this? P. On to the next question. I'm not gonna read the little fun fact, but here's the question. Someone cracked a joke saying that platypuses are even slower than manatees. Naturally, you decide to analyze the validity of the joke because you're a party pooper. You randomly select 200 platypuses. You want to be really, really sure and record their speeds. you find the mean speed of these platypuses to be 3.6 miles per hour with a standard deviation of 3.1 miles per hour. You randomly select 156 manatees and find their mean speed to be 3.9 miles per hour with a standard deviation of 2.8 miles per hour. Now let's just think about what this Excel spreadsheet would look like first. I'm going to tighten this up. Cropped up. So your Excel spreadsheet, just because I find that that's the easiest way to visualize it, right? Do I have one sample or do I have two samples, right? And so you would have your platypus speed in one column, and then you would have your manatee speed, right? Platypus 1, manatee 1, platypus 2, 3, blah, 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 blah. But you would have 200, n equals 200 platypuses, and n equals 156 manatees. Right? Of those, all right, let's do a little P and an M on here just to keep track of which group it's from. Of these below, I can find the mean, or we found that the mean speed of the platypuses was 3.6. Right, so if you imagine your spreadsheet, then you know how to find the average of something, right? Equals average, and you take all those data points and it'll return it. The standard deviation, stdev dot S, I think it is. Right. So the sample standard deviation of the platypuses was kind of high, 3.1. Right. A lot of spread around that 3.6. Same thing with the manatees, but now you have a sample of size 156, right? And so then X bar for the manatees, the mean speed for the manatees was 3.9. And the standard deviation of the speed of the manatees was 2.8. So this, there are a couple of different clues, but this for our question type must be two independent sample means. And I like to emphasize the independence. You could just say two sample means, but I like to emphasize the two independent samples just to show that these are separate, and that's okay, right? We just want to compare these two speeds. And so for our type, the type of question, this is two independent sample means. Right, we want to compare those two means to each other. Right. Another clue is that I have two different sample sizes, right? And so it has to be independent. I can't pair those anymore, right? And so here, no natural pairing. So here's the reason, which you don't need to say, but it's nice to know why. No natural pairing, and NP is not equal to NM, right? Different sample sizes, which is a good clue as to why it's two independent sample means. Okay. I'll put, let's see if I have, hey. Yeah. I guess we should check our conditions before. Oh, they're so boring. Am I allowed to say that? I don't know. For two sample means, right? I have to check the conditions for each group. but also make sure that the groups are independent of each other, right? Which again is one of those things that, well, that's how we determined what type of question it was. And so I'm going to make it optional for that reason. Okay. And so step 0, check the conditions. Independence. As long as each group was randomly selected, startled myself, was randomly selected, we can assume that they're independent, right, within each group. But then we also need independence between the two groups in order to do the analysis we're about to do. You randomly select 200 platypuses and you randomly select 156 manatees, right? And so we can assume that within each group, we have independence, right? But we also, oh, she's got it. Sorry, I could have got it for you, but you were so quick. I saw you were on the move already. Each group was randomly selected. That's probably good enough, but therefore we can assume all platypuses are independent of each other. And all manatees are independent of each other. Right, we need to check it for both groups. And again, this one's optional just because it speaks to the type of question, right? And so you've already determined that, hey, these two samples, there's no natural pairing, right? And so I'm going to treat them as two individual groups, right? Or independent groups. The groups are independent of each other. So there's kind of within group independence and then between group independence. But this is because it's a 2 independent sample means type of question. And then the normality condition, both our sample sizes are larger than 30, and so we may assume normality, right? We had 200 and 156, so both of those we can assume normality. Both sample sizes are larger than 30, so we may assume normality. Therefore, the conditions for inference are satisfied. Now we're ready. Part A. Is there evidence that platypuses are even slower than manatees? So slower than manatees. Okay. Use a formal hypothesis test with an alpha level of 0.1. Let's go to our formula sheet because we did a lot of work trying to pick what type of question we have. And we said, okay, 2 sample means or 2 independent sample means. I like to emphasize that. Then we're working here on your formula sheet. Right? It's bigger because we have 2 groups, information from 2 groups. but the procedure stays the same. This here is just theory, so just as always, you can kind of ignore it, right? It's what we're using down here. Okay. But we want to do a hypothesis test, which means that we're down here. I'll do this version of the null hypothesis, but only to show you what the inequality would look like, right? But if you prefer this version, that's totally fine. I'm happy either way, okay? It would be kind of weird if you used one for the null and another version for the alternative. That'd be kind of weird. So don't do that, but because it's still technically true. Step 1, state the hypotheses. And I've already warned you that I am going to mark test 2 pretty hard. That's how you learn your lessons. But then I can be really nice on the final exam. Because then there's no more lessons. But it hopefully makes my marking, and that's all I care about, I guess. No, hopefully it helps you learn for the final exam, and then I always find it, so I have a hard time taking marks off, but I always find that if I don't, then you don't learn. I know. I promise I'll learn my lesson. No. I'm gonna say mu1 minus mu2. What's my error here? I need question specific subscripts, right? Especially when we're talking about, okay, our platypus is slower than manatees. If I say that mu1 minus mu2 is less than 0, that doesn't mean anything unless I've attached which group is which here, right? And so here, I'm gonna highlight this. It's okay. Right, we need question-specific subscripts, and I think I had the information as platypus, then manatees. Now, as in the 2 sample proportion case, it doesn't actually matter which one you make group 1 and which one you make group 2, as long as you're consistent throughout, okay? And so I'm gonna make this group 1, my platypuses are group 1, and my manatees are group 2. Okay? And so my platypuses minus my manatees. Oh. For my alternative hypothesis, I have to hypothesize about mu p minus mu m, right? That stays the same. And how does that relate to 0? Okay. But now I need to think about, okay, if the mean speed, so if the mean speed of the platypuses is slower than manatees, that means that this value is always going to be bigger, right? And so then I'm subtracting, and you can, I always kind of toss in fake numbers, right? 2 minus 3 makes a negative, right? And so then it has to be less than 0. Okay. Or if you prefer, you could say mu1 or mu p, let's say, is equal to mu m. And then it makes it a little bit easier to set up your alternative hypothesis, right? Because you want to show that mu p is less than mu m. And then you don't have to think about, okay, the difference compared to 0. Either way, you've got a one-sided test, right? You're only concerned about one extreme. So this is a one-sided test. Step 2, do the test, do the do. So now we have to calculate our t. And I guess maybe I'll do it down here so I have the whole. Whole width of the page. X1 bar minus X2 bar divided by the square root of S1 squared over N1 plus S2 squared over N2. So here, I've dropped the question specific subscripts, but it is expected that you keep the same order. So platypuses will be group 1 and manatees will be group 2. But this is really annoying to write out with question specific subscripts. So I don't expect that. You don't have to do that. You do have to do it in your hypotheses. And then you keep that same order. So let me see if I can snag this information because we already summarized this. Copy. Paste it here. Let's say group 1 is the platypuses. And group 2 can be the manatees. This information, right, this summary information lends itself to being put in a table. And so often I do report it in a table, but it's nice to see it in a kind of a word problem scenario as well. Okay. Plug and chug. T is 3.6 minus 3.9, right? How far is that difference from 0? Divided by 3.1 squared divided by N1, which is 200, plus 2.8 squared divided by 156. Take it nice and slow here. 3.1 squared divided by 200. And then usually I like to store that. And then 2.8 squared divided by 156. And I'll add that to my stored value. I get 3.6 minus 3.9, which I guess is negative 0.3, divided by the square root of 0.09830641026. Everyone loves to forget that square root though, so that's why I'm, hey, where did that go? Oh, down here. The heck? You gotta clean that up there. So then once I take the square root of that, I get negative 0.3 divided by 0.3135385307. Now for my records, because I suspect I'm gonna have to build a confidence interval, I'm gonna store this in A because then I can just bring it in later, right? Just in case. And you can read ahead through the question and see what you need to do. But this means that the standard error, which I'm gonna stored in A. And then I'll just do 3.6 minus 3.9 divided by that guy. I get a T of negative 0.956820201. Boring. Why is that boring? Because we don't get to reject H naught. I can already tell, right? Usually we need to move out 2 standard errors before we start rejecting H naught. But we'll confirm in step 3. Find the p-value. Using the t-table with degrees of freedom. And because we have 2 samples, right, we have to use this kind of bigger formula. But remember, all it's saying is the smaller sample size minus 1. So if you don't like this formula, you can use words, right? Using degrees of freedom, smallest sample size minus 1, which would be 156 minus 1, which would be 155. But using blah, 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 right? You can say it in words if you prefer, but I'm going to use the shorthand so that you can get used to it, because I think it's going to save you a lot of writing. Minimum of n1 minus 1 and n2 minus 1, which is the minimum of 200 minus 1 or 156 minus 1, which is the minimum of 199 and 155. Well, the minimum of 199 or 155 is 155. But I also happen to know there's no 155 line on my t-table. So I have to say, but using, I'll grab the table. 155, 80, 100, 1000. I have to use 100 degrees of freedom. Oops. Helps if I include the 100. But using degrees of freedom equal to 100, right, on the table. Puts me here. Then we find, I can't resist kind of leading into it somehow, the absolute value of t equal to negative 0.95682, inconsistent with how many decimal places, but as long as you have at least 3, you're safe. Is between 2 values. Now, I dropped the negative 0.95682, puts me somewhere here. So I write those down, somewhere between 0.845 and 1.042. Now I've seen mistakes happen, especially in a test situation, right? If you tell me that it's between 1.042 and 1.290, that's wrong, right? But as long as you follow through with those numbers that you gave me, then I'll take half a mark off for doing it weird, right? Your eyes skipped a beat or something like that. But as long as you're telling me all the things that you're doing and what you're doing makes sense, then I'm happy. Okay, so it's not about the numbers or anything like that. It's about the concept. And do you have the spirit of it? More the spirit of the law than the letter of the law. So then we have a one-sided test or a two-sided test. Go all the way back up here. I want to know if it's less than 0, which means I have a one-sided test. So my one-sided p-value is between 0.15 and 0.2. Now I'm ready for my conclusion. Say all the things that you know. Since our one-sided p-value is between 0.15 and 0.2, you just did all that work, you may as well say it, right? And is that less than 0.05? It's not less than 0.05, right? And so let's write that down. Since our one-sided p-value is between 0.15 and 0.20, it is not less than our alpha level, even though I think I remember it being a little bit higher, making it easier to reject H naught, but still not easy enough. 0.1, stay flexi. Alpha level of 0.10, which means we do not have enough evidence to reject H naught, which means we do not have enough evidence to reject H naught. Notice the symmetry, right? If it is not less than our alpha level, then we do not have enough evidence to reject H naught. What does that mean in terms of the question, right? You can reword the question as an answer. So I'm gonna snag it here. Is there evidence that platypuses are even slower than manatees? No, there is not. Whoa. Therefore, there is no evidence, or there's not evidence, whatever you want to say, that platypuses are even slower than manatees. In fact, our hypothesis test showed that, well, they move at roughly the same speed, right? There's no significant difference in their average speeds. Nice. Whew, these big mumbo jumbos. I think there's a part B too, but what time is it? I'm suspicious because I thought I had another hour, but I do not.
Yeah, 11:42, just like verify.
Yeah, I'm like, the math's not coming, but no, it's not. That's what startled me.
It's 11:42 and that.
Oh, it's a little bit of, yeah,
Little bit.
little bit ahead, but yeah, that's okay. Okay, now I'm done with this page, so I'm gonna delete this because I've moved it all around. Okay. Whoa. Maybe I'll do this one on a fresh page. Just like before, we actually know the answer already. We've already determined that there is no evidence of a difference in the speeds, right? And so now, is there evidence that platypuses are even slower than manatees? Use a 99% confidence interval to test the hypothesis. So now we're going to make a confidence interval. Now, a couple of things. Confidence intervals are going to have the same conclusion as a two-sided test, right? But we did a one-sided test. Okay? And so here, our confidence interval is going to be equivalent to a two-sided test. Okay. In fact, a two-sided test, and if we have a 99% confidence interval, I have 1% left over, okay? Which means that my 1% or 0.01 is split evenly amongst the tails. And so then 0.005 here and 0.005 here. This 99% confidence interval should match the results of a one-sided test with an alpha level of 0.005, not just 0.05, but 0.005. So they're not necessarily going to match anymore. All right, so let's just do it and see what happens. Can I, in the interest of time, say, recall that the degrees of freedom is 155, but using 100? From part B or from part A? Because we need our degrees of freedom to find our T star, our critical value. We've got our null and alternative hypotheses, but we do want to test the hypotheses, and so we have to state them again. Mu p minus mu m is equal to 0, and the alternative is that mu p minus mu m was less than 0. This is kind of bad. And maybe I should edit it. Is there evidence that platypus speeds are different than manatee speeds? Edit that a little bit. Then I would have a not equal to here, which is really the only thing that I could answer with a confidence interval. It has to be a two-sided test. Maybe I'll clean this up here. Okay. And so in order to use a confidence interval, it should be a two-sided test. That's an oversight. But now, for my confidence interval, I have my point estimate plus minus my T star. And then this S1 squared over N1 plus S2 squared over N2, I'm going to say, recall that this whole thing, standard error, is stored in A on my calculator, obviously, but I'm going to reuse that so I don't have to actually do that math again. Now, if you end up doing that and your first one was wrong, it's okay, I follow through, right? And so it's not about the numbers, it's about the concepts, because numbers can be tricky. All right, we had a difference of 3.6 minus 3.9, I seem to remember. Now you can play around with 3.9 minus 3.6. The standard error stays the same, right? You've just kind of moved your A plus B is the same as B plus A. And so then you would be working with a positive difference if these were switched around, but the interpretation of the differences would stay the same, right? It's just how you've set up your difference. Now I need my T star for a 99% confidence interval. 99% confidence interval, and I'm using 100 degrees of freedom, 2.626. Oops. I'll jot that down up here. 2.626. 2.626. Now, even when you are using values that you've stored, you should still write out what you should be doing. Otherwise, it's really hard to follow, right? And so we had 3.1 squared over 200 plus 2.8 squared, I think it was, over 156. But then I'm just going to go for it. 2.626 times recall A. And hopefully I didn't overwrite it. I get 0.8233521817 and negative 0.3. Negative 0.3 minus that guy. I get negative 1.123352182 up to negative 0.3 plus 0.823352. Quicker to just write it out, 0.5233521817. We'll interpret the interval. We are 99% confident the interval from negative 1.12 to 0.52 captures the difference in mean speeds, right? As opposed to the mean of the differences before in the paired data, captures the difference in mean speeds of platypuses versus manatees. Now, since 0 is in this interval, we do not have enough evidence to reject H0. Since 0 is in this interval, we do not have enough evidence to reject H0, right? That the mean difference is 0. Therefore, no significant difference in speeds. Because I'm way out of time. But there's a whole other page. They're shorties. I'll post the solutions, but I encourage you to try it. And then I'll post it before I'll add it before I upload the notes from today. How about that? Make it look like we did more than we did, but we did a lot. If you have any questions, let me know. Otherwise, enjoy your weekend and see you for the test on Wednesday. Eek. You're excited to show me everything you know.